Hello, I'm Swati. I'm a developer at Uniprot. I'm excited to talk to you about Nightingale, an open source visualization library for rendering protein related data. This is in collaboration between Uniprot, Interpro, and PDB at Embl EBI. So, what is Nightingale? It is a library of standard web components. It is mainly specially designed for rendering protein data. It is useful for rendering sequence structure, sequence features like uh, domains, regions, variants, in PTM data, proteomics, and even structural data. It uses a track-based layout where the sequence is displayed horizontally, while the other different data types are layered in tracks that can be stacked vertically. So this allows users to compare different annotations and interpret different annotations in one integrated view. Since Nightingale follows web component standards, it is highly interoperable. You can embed this within other native elements or other standard components within the same page, irrespective of the underlying framework. It could be not attached to React or Angular or anything. It can be used anywhere. Here is an example of Uniprot's ProtVista tool. It uses several Nightingale components. The data you're seeing is from Uniprot itself, and this interface allows flexible customization. You can align the tracks as you want. You can tailor the tooltips as you wish. Yeah, let's break it down a bit. I have highlighted a few rectangles here. They are called tracks. They are the basic fundamental building blocks, like Lego pieces. You can mix and match them as per your data needs and requirements. There is no one good way or right way to assemble them. Each track can be used individually, or they can be combined to make like a powerful tool like this as well. Each track is responsible for rendering its own data. So if you take variance data, it fetches the data and then it renders the visual. It is self-contained. Even the structure viewer here is also considered as a track. It's basically viewing the structural data in a 3D context. The viewer can be built with minimal number of tracks or any number of tracks as you want. The example that you're seeing on top is from Uniprot's entry page under families and domain section. Here we just need to view the domains. So we have got navigation to navigate the viewer, and then the domains itself, and that's it. While the bottom example is from Interpro. Although it is styled differently, it is built on the same Nightingale components. And similarly, PDB has its own adaptation of Nightingale components in their protein viewer. So how do all these tracks stay in sync? Here comes the Nightingale Manager. So it's like a container for all these different Nightingale components itself. So its main responsibility is to keep all these tracks in sync, like in interactions like highlights, zoom levels, and etc. If a user clicks on a variant in a variant track, this track emits a highlight event. In this case, it's 363, the selected coordinate. And then the manager captures the event, and then it broadcasts it to all the tracks, basically setting the highlight attribute of all the other tracks. This creates a synchronized view. Even though the tracks do not communicate with one another and not aware of one another, they are all showing the same view. You can see the same, the yellow highlights in each and every track, but they don't know about one another. The manager is the one responsible for taking care of it. This is handled using standard DOM event propagation and then attribute setting. These are the technologies that we use. They're using Lit for building our web components. And we have both SVG and Canvas-based graphics in Nightingale. We're using Canvas in our heavily used tracks, mainly for boosting performance. Wherever we are using Canvas, we have got SVG on top just to for interactivity purposes to capture the interactions. This is not critical for performance. Here's where Canvas matters. If you take this heat map here, this one is rendered using Canvas. Canvas is basically, it draws pixel onto bitmap image. So how you can measure performance is by the dimensions of the image itself. Whereas if the same thing is rendered in SVG, it will mean like for these 1,000 data points, we'll have like 1,000 DOM nodes. Whereas in Canvas, we have got like one DOM node, which is the image itself. So it reduces the memory overhead for the browser, and it's very, very fast. We have benchmarked the performance for both SVG and Canvas. The one on the right side, is for the initial load time. Canvas handles up to like 1 million annotations in under 1 second, which is like 100 times faster than SVG. While on the one on the left is comparing the same with interaction time. Whenever the user interacts with the viewer, the response time matters. So at that time, the ideal threshold is not 1 second. It will be considered too slow. So we are considering less than 100 milliseconds. And Canvas is good at handling up to like 100,000 annotations under 100 milliseconds, which is still faster than SVG. Especially when it is zoomed in, you see the green cross there for Canvas. It is way, way faster. And we're still migrating some of our components into Canvas. It's still work in progress. As I mentioned, Nightingale is fully open source, and we are very open to external contributions, collaborations, and we're also actively looking at other visualization libraries, integrating the best practices into our work. If you would like to explore the components itself, here is our link to the demo. As I mentioned, it's a collaboration with Interpro and PDB. AnyProd itself is a consortium. We have got teams working across 3 sites. We are based in EMBL ABI, and we have got people at ISMB in Switzerland and PAR in the USA. And we are very grateful to our funders for supporting this work. Lastly, we highly encourage you to click this link. We have got some survey for UniProt. If you're interested in user studies, if you're a keen user, could you please click this link and let us know your feedback. Thank you.
Thank you very much. Do we have questions? Let's see a question in the very back of the room.
Yes.
Thank you. Very impressive here. Just wanted to ask whether it's possible to cluster the tracks that you mentioned.
Cluster the tracks.
Yeah, from different analyses.
You can, from different analyses, different data?
Different, yes.
Different data sets?
Different data sets or different protein analyses, yes. Or like from one, analogous analyses, but from different, let's say, proteins or
you can view one protein at a time, but the protein data source could be from different, because we have got data schema that as long as your data is adapted to that schema, you should be able to view it.
Okay, thank you.
Thank you. Okay, let's thank our speaker again.